So now that we know that the transformer is built out of two parts, the encoder and the decoder, we will start layer by layer from the beginning to understand what each component of the encoder and the decoder are. And the first one is going to be the input embedding. In transformers, just like in many other neural network architectures, the first step involves converting words into numbers. The words are first tokenized. That is, each word is matched totally or partially with a token. In our course of building a tokenizer from scratch, we learned that the tokenizers are the bridge between humans and computers at a very basic level. Tokenizers just convert a word into a number. Again, words are converted into tokens. And each token is associated with a number called a token ID. This token ID will usually go from 0 all the way up to the number of tokens that the model can handle. Let's look at this example. Let's take the phrase "red rose means love." The tokenizer will take each one of these words, or actually subwords, and convert them into tokens. In this simplified example, we are defining that each word is a token. Production-grade tokenizers actually split words into subwords. But for the sake of understanding this easily, let's say that each word is one token. So we take the phrase "red rose means love," we split it in its tokens. As you can see, we have some special tokens, one at the beginning and one at the end, and we map each one of these tokens with a number. So now the words of a human were converted into numbers that a machine can start understanding. Each token ID is in turn associated with a vector called embedding. The set of vectors of all tokens is called the word embedding matrix. Here is where the magic of transformers start to happen. These vectors, which were learned in the training of the transformer, have learned what its tokens mean, what it represents. These vectors contain now the meaning of the words, or the meaning of each token. In any language, words carry context, sentiment, and syntax. Word embeddings encapsulate these attributes, enabling algorithms to discern the relationships and meaning among words. In my opinion, word embeddings are almost the brains, or at least one main repository of the knowledge of the transformers. So, every transformer has a word embedding. We will have a next course where we will go deep into word embeddings. This part of the embeddings is very important that we understand it perfectly. So let's go again step by step. First, words are converted into tokens. Next, tokens are converted into token IDs. And now, each token ID is turned into a vector. The word embedding matrix that we saw in the previous slide is like a lookup table. Given that each token ID is represented in this word embedding matrix, what we do next with the token IDs is look for the respective vector of each one of the tokens in the order of the sequence. So once we have matched each one of the token IDs with their vectors, now we have the vectors that represent each token of the input. And this is what is called an input embedding. So, where are these numbers coming from? Embeddings in transformers are learned during training, and they capture the nuances of the language as per the training corpus and objectives. In transformers, the embedding layer is, at the end of the day, a lookup table that translates token IDs to their corresponding vectors, which is a very powerful lookup table, if you ask me.